Hello again. This is Math 2270 coming to you from the College page, and the title of this lecture is Turning Equations Exact Using Integrating Factors. As always, please be an attentive listener while watching this video. By way of introduction, previously we saw that there are powerful ways to solve exact differential equations, but many differential equations are not exact. But recall that we can solve linear first-order differential equations by introducing an integrating factor. In this lecture, we explore the ways and means to use an integrating factor approach for certain non-exact differential equations. And sometimes, in this way, we're able to render a non-exact equation exact. So continue to recall that a differential equation of the form m of xy plus n of xy times y prime is equal to 0. Now sometimes this y prime is written as dy dx, and sometimes we just have a dy there and dx here, but that's a different manifestation of the same differential equation. So a differential equation like this is exact if, and this was the test that we proved in the other video, if the partial of m with respect to y is identical to the partial of n with respect to x. And that in such case, we could always find, by the technique of exact equations, a psi of xy equal a constant, and this is an implicit solution of that form. And psi, the partial of psi with respect to x is m of xy, and the partial of psi with respect to y is n of xy. Now, even if this equation up here is not exact, it is sometimes possible to multiply it by another function of x and y to obtain an equivalent equation, which is exact. That is, one can sometimes find a function, mu of xy, such that mu of xy times m of xy plus mu of xy times n of xy times y prime is equal to 0, and this equation here is exact. Now such a function is called, mu of xy is called an integrating factor. The I is missing here. If an integrating factor can be found, then the original differential equation, this one, can be solved by constructing a solution to the equivalent differential equation, which is this one. So this is kind of a good approach. Let's see where this leads us. But first, let's do an example. So consider this differential equation here that we have. So this is x squared y cubed plus x times the whole of 1 plus y squared times dy dx is equal to 0. Now, let's check to see if this is exact. So we take the partial with respect to y of this one and get 3x squared y squared. Then we take the partial with respect to x of this one, and we get 1 plus y squared. So this is not exact. But what we're going to do is multiply both sides of this differential equation by an integrating factor. In this case, this is mu of xy equal 1 over xy cubed. Now, this is magic right now, and so in fact, this is kind of an inspired choice, but just see how it works. So if I take mu of xy equal 1 over xy cubed, then what I'm going to get is this multiplying all the way through by mu. I get x plus 1 plus y squared over y cubed dy dx is equal to 0. Now, you could check, but you see the derivative of this with respect to y is 0. The derivative of this with respect to x, again, partial derivatives, is equal to 0. So this is exact, but it's also even a separable differential equation. And so we can calculate the solution to this by integrating both sides. And then we'll integrate both sides, and we have a constant of integration. So we add 1/2 x squared and minus 1 over 2 y squared plus ln y. And the reason this is minus is because you had to move this to the other side plus lny, and this is equal to the constant. So you see, we have solved this by introducing an integrating factor. Now, in general, the problem of finding an integrating factor mu of xy for a given differential equation is very difficult. But in certain cases, which is what we're going to discuss today, it's rather easy to find an integrating factor. Okay, so let's again consider a first order differential equation here, and we're just going to assume that there exists an integrating factor, but now we're going to say suppose the integrating factor only depends on x, not x and y both, as in our example. So mu here is going to equal mu of x. Now if it's really an integrating factor, when I multiply all the way through by mu of x, our original differential equation, this has to be exact. That means the partial of this one is equal to the partial of this one. So now we're going to use the differentiations and we're going to take the derivative with respect to y here and x here. And we're going to use the product rule, but we're also going to use the fact that mu of x depends only on x. That means it is a constant with respect to y. So when we do take those derivatives, we will get this mu partial of m with respect to y is equal to the partial of mu with respect to x n plus mu, and this is the partial with respect to n x. And if we reorganize this, solving for d mu dx, we get d mu dx is equal to 1 over n, and here we have the difference between the partial of m with respect to y minus the partial of n with respect to x mu. And if you look at this for a while, you realize that, since mu depends only on x, then this derivative also depends only on x. So you see, this really is a first order linear differential equation if we set p of x equal minus 1 over n. Notice you have to move it to the other side to get it into our standard form, the partial of m with respect to y minus the partial of n with respect to x. So you see, with this being our p of x, we just have to solve this first order linear differential equation to get our integrating factor. And we know the integrating factor is mu of x is equal to, and this is a constant, times e raised to, and this is the integral of minus p of x dx. That's the integrating factors that we talked about. But since p of x was this is a times, and here's the integrating factor that we have. And so the formula here gives us an integrating factor for our non-exact equation as long as this depends only on x. Now, it wouldn't surprise you to see that we could do the same thing if we have an equation that is not exact, but we can try to say what happens if we can explore and see if there's an integrating factor that depends only on y. So again, consider the first order differential equation shown here. And suppose there is a mu where it's only a function of y. So mu equals mu of y. Now, if mu is really an integrating factor, you can multiply all the way through by that, and that's exact. That means that this partial is equal to this partial derivative. So when we carry out the differentiations, using again the product rule and the fact that mu of y depends only on y, we get that we need to solve this first order linear differential equation. And again, since mu depends only on y and not on x, then this depends only on y, and so we can p of y equal this expression, and we can rewrite our differential equation as a linear first order differential equation, d mu dy plus p of y mu equals 0. And so mu of y again is this integrating factor. And so we can come up with an integrating factor as long as this expression depends only on y. So summarizing then the ideas about integrating factors, we are trying to solve something m plus n y prime equals 0 that is not exact. But what we will do is we will calculate f1 and f2. So f1 is this expression, and if this f1 expression, the partial of m with respect to y minus the partial of n with respect to x, depends only on x, and notice you did divide by n here, then this expression, integrating that f1 expression, e to that f1 expression, will give you your integrating factor for the original equation. Similarly, if what we call f2 here, that's the partial of n with respect to x minus the partial of m with respect to y over m, depends only on y, then mu of y equals, and we just exponentiate this expression, will be an integrating factor for our problem. Now, if neither of those conditions are true, then it's a very difficult problem, and there's little hope of constructing an integrating factor, although I did show you that it can be done, but it is largely a guess and check. Let's do an example then of this. Okay, so suppose you have this equation that you're solving. So here is the m of xy, and here's the n of xy, and notice that now I've written this, instead of writing y prime over here, I make this into dy, and I put dx over here. Okay, so m of xy is the coefficient of dx, and n of xy is the coefficient of dy. Now, when I take the partials, what will happen is the partial of m with respect to y is 3x squared plus 2x plus 3y squared, and when I take the partial of this with respect to x, I get 2x, and those two things aren't equal, so the equation is not exact. So we need to find a function mu such that I can multiply all the way through and make it exact. But what we've learned is, if we look at the f1, which is the partial of m with respect to y minus the partial of n with respect to x over m, and see what we get. So when you do those calculations, you will get 3. Now 3 could be thought to be a function of x only. It could also be thought to be a function of y only, but we really want it to be a function of x only. So 3 is there. Now when we check f2 though, do the calculation. Now in this case, the f2 is the partial of n with respect to x minus the partial of m with respect to y all over n. We do that calculation, we get this expression in x and y, and you see this is a function of x and y. It's not a function of y only. So when we look at this, we realize that since f2 depends on both x and y, we can't construct an integrating factor depending only on y from it. However, since f1 does not depend on y, we can consistently construct an integrating factor that is a function of x alone. So we're going to say mu of x is equal to the integral, actually the e raised to this integral, and when I integrate the 3, I get e to the 3x. So now we're going to use this as an integrating factor. So we'll multiply all the way through by e to the 3x here and e to the 3x here. Now, if you check, you'll see that the partial of c with respect to x is this, m of x, y, and the partial of c with respect to y is this. That's what we have to find. Now, if we go through the process, as we discussed in the video, of solving this, we'll end up with c of xy is equal to h1 of y plus x squared y e to the 3x plus 1/3 y cubed e to the 3x. And also, if we integrate the second one with respect to y, we'll get a function of x here. Now, when we compare these equations with these partials, we can see that h1 of y equal h2 of x equal a constant. Therefore, our solution to this equation this equation up here is this, and that means it also must be a solution to our original equation. So the solution is of the form psi of xy equals e to the 3x x squared y plus e to the 3xy cubed plus a constant. And if this were an initial value problem, we could figure out what that constant in fact was. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself because self-care is important. And take care of each other because we're all in this together. God bless.